is Dave Hughes. I'm the CEO of HTC Embedded. I'll just give you a quick overview of the what I'm going to talk about today. First, I'll give you a very brief introduction to HTC Embedded. Wolfgang's covered that quite well already, so it'll be extremely brief. And then I'd like to go into explaining what we mean by safety software. After that, we'll take you through a very high-level view of the safety software development process as we see it. And then comes the key part of the whole presentation, which is a practical demonstration of how safety software development works in contrast to how a standard development might work. And then we'll wrap the whole thing up with a quick concluding comments at the end. So as Wolfgang mentioned, HTC Embedded is a specialist, deeply embedded company. We've been developing software elements for use in deeply embedded systems since 2002. We focus very much on file systems, fail safety, flash management, networking, and USB components. And we develop things in standard ways. Like most development companies, we provided software which we regarded as very high quality. We did a lot of testing. We spent a lot of time focusing on support. But in the end, there's a different level of software, which is what we classify as safety software. If you go to, many years ago, NASA created a study which showed that to produce code of defect rates that were acceptable for use on NASA projects, it cost something like $100 a line to produce. Siemens had a similar study which was working on something like $10 a line to produce. Either way, to produce very high quality levels of code is very expensive business, and that's most people not really willing to pay that for use in standard products. But there are markets and environments where people are willing to make this investment, particularly in automotive, aerospace, industrial. And for the last 5 years, HTC has been very much focused in changing from a standard development approach to focusing on these markets and developing software to standards and to these levels of quality. And the purpose of today's presentation is to share some of the core differences we see that you experience when you move from being a standard developer, developing what you consider very good software. You spend a lot of time testing, specifying it, coding it, analyzing it. But in the end, safety software is another level of investment when you're going to produce it. So what do we mean by safety software? The development of software standards or development of products in different industries has been completely verticalized. So there are different standards for aerospace, automotive, industrial, medical. These are to list a few. Even nuclear, trains, they all have their own standards. And the reasons for this are quite clear. In industrial safety, the aim was to make a system safe. So if anything goes wrong, you simply switch it off, make it in a safe state, shut the door, stop the drill. However, in a car, you can't just fire the airbags every time something goes wrong. That is just a too radical reaction. And in a plane, you can't just switch off everything. So you have to have different attitudes to safety based on the actual environment, the actual use case of your equipment. And this is why these standards have become verticalized. But in practice, when it comes down to software development, they've all come down to roughly the same conclusion of how to develop software. And basically, the V model is the gold standard for this. Software needs to be developed in a very rigorous and structured way. NASA started a lot of this development off in the 80s, maybe even some of it earlier than that, working out how to create low defect rates in software. 61508, the industrial standard, was a milestone in developing this, and then other industries have continued to build on this. In the end, there's one conclusion: to develop software to a much higher level, you need to adopt something akin to the V model, if not a strict V model. There are variations on it, but in the end, the fundamental principles are the same. Software in itself, safety software in itself, cannot make a system safe. It has to be taken in the context of the whole system. It has to be integrated and validated in the system. But having a safety developed software component gives you a chance of making your whole system safe which is not practical if you do not take this approach. So for us as a company developing embedded software, we have three goals, three things we want to achieve from our safety software. The first goal is to achieve completeness. That means that the product does exactly what it says on the tin, no more, no less. So we want to make sure that the product is complete. You pick up the specification, the manual, and there is nothing in there that isn't implemented, and there isn't anything in there that there isn't anything implemented that isn't in it. It has to be complete. This is our first goal. The second goal is to make this code maintainable. We want to be able to, going forward, customers change their requirements, technology changes, particularly in our industry, in deeply embedded. Moore's law continues to thrive in flash, in microcontrollers, in every different area. We keep on developing. So the code needs to be maintainable. And this third part of it is the whole computer industry over time, over the last 40, 50 years, has been built upon reusable components, be they CPUs, be they RTOSs, be they networking stacks, be they Java apps, object-oriented programming. The whole thing is built on the idea of being able to reuse components so we don't have to keep starting from scratch again and again. And what we want to be able to do is reuse safety components in exactly the same way. We don't want to have to start thinking about every component again, every time it gets used in a different car, in a different plane, in a different train, etc. We want to find a way of reusing these components. For that, we need to take quite strict development methods. So as we've already mentioned, the V model is really the only show in town when it comes to structured, safe software development. The V model, practically every safety presentation that goes to any depth at all will always have a V in it somewhere. It's kind of necessary to do it. The basic concept is quite straightforward. You work from the left side of this diagram to the right side, going down, time is progressing. You start with the concept, you specify it with requirements, you build an architecture, you do a detailed design, you implement it, and then going up the right-hand side, you're verifying each of those steps that you've gone through to make the whole system complete. Various people propose different methods of doing this, but in the end, the net result has to be that every element of the design implementation architecture can be verified some way or other, and there's some traceability in this whole system. So that is how we achieve completeness in the system. We can make sure that every requirement is tested, every test matches a requirement, and every part of the implementation matches the test. Then we come to the second step, which is the maintainability of the software. For this, we need full software lifecycle maintenance. And that means we have a kind of cycle we go through that if somebody raises an issue, they want a change made, first you have to do an impact analysis. An impact analysis is only possible because of the V model you implemented in the first place. This gives you the basic artifacts that you can trace between test cases and requirements and the architecture and the architectural design and the code implementation. The only way you can do an impact analysis of the change requested is because all this information is tied together in a structured way. Once you've done the impact analysis, you can then integrate the necessary changes to make a change. You can then go through a verification validation process of those changes, again, back into the context of the V model. You can then deploy them, and then you go back into your maintenance phase. This whole maintainability is entirely based upon the fact that your original development had the basic artifacts created by this V model development. And then we come back to reusability. Reusability is advocated in all industries. There is simply no need to redevelop things. Even across industries, it makes very little sense. A TCP/IP stack is a TCP/IP stack, whether it's in an aeroplane, whether it's in a car, whether it's in a train. The implementation and requirements may be slightly different, but there's no real verticalization of these things. So to make them reusability, to avoid reinventing the wheel develops, it gets more and more advanced over time, but there's no need to start reinventing it all the time. In industrial safety, in 61508, they had the term COTS. I don't particularly like the term COTS, custom off the shelf, simply because it's used in so many industries in so many ways, but there's quite a good definition of how to implement a reusable component or an external component to be integrated to your safety project. In medical, they use the term SOUP, which is software of unknown provenance, or pedigree. Personally, I don't like having the term unknown in the middle of my safety project. I find this a bit uncomfortable. But I think the guys who nailed this and got this into much better shape altogether were the automotive guys who went for the safety element out of context definition, which is included in the 26262 specification. And this defines how to create a software component independent of the particular vehicle that's going to be integrated with, or the particular item in a vehicle, and creates the whole environment. I think there's a very clear definition in there of how that can work. They actually give about 4 different options for this, including a proven in use case, which I don't really support as a method of doing software verification, because it's extremely difficult to show how a proven in use can work with software. But the concept of how you would develop a component in the same context of a vehicle, any other piece of software in the vehicle, and reuse that, I think is a very good work-through case. And we'll explore that kind of approach a little bit more going forward in this discussion. Excuse me. So because it's a reusable component, we need to base the component on a set of assumptions. In the standard safety model for a V model, if you're developing cars or functional safety, you don't have assumptions in this way, in that you define the whole vehicle, you actually define everything. But because you're making a component for reusability, you have to define the working environment for that. So to do that, you need to specify a complete set of assumptions. The assumptions of the operating environment which your software component is going to work in. Some simple examples of that are the endiness of the microcontroller, what the RTOS is, how it behaves, is it preemptive, etc. What supporting functions the system has to provide to be able to run this particular module. What hardware interfaces are available, need to be available, what quality are those hardware interfaces. These are all things that need to be specified when you develop your safety software, so that you know when you go and reuse it somewhere else, you can validate these assumptions as a starting point for integration with your new target. Once you've done that, you can now go on to developing the real specification of the product. So in safety terminology, this is the requirement specification, which starts at a very high level, and then you go down, drill down into deeper and deeper requirements until you get the detailed functional requirements. Requirements can act as the specification of your software. They are the specification of your software, but they're also something you can share with your customer, with your integrator, to show this is exactly what we have decided this module is going to do, this component is going to do, based on the original contract that you started developing this to. This can also act as a very good starting point. This is the source of the user and the safety manual for the system. And the other part is that once you have the requirements, you can derive the test cases from that, which we'll come on to in a minute. To manage requirements, typically you use tools to support you so that you can document them and make links between requirements, etc. Typical tools for doing this include IBM DOORS, is a kind of an industry standard, but there are many, many more tools for doing this that you should investigate. And then I'm going to skip the V model a little bit here, because the point of this presentation isn't to go into a very detailed analysis of the V model and everything that needs to be done in a software development. You get to the implementation side of the system. That includes from the requirements, deriving an architecture for the system, then deriving design, a high-level design, possibly in some graphical language, and a detailed design, maybe in some semi-formal language. That design and architecture needs to be traceable to the requirements. And then you implement the code. The code is directly derived from the design and hence traceable. From the code and the implementation, you'll then, so you get these unit implementations that you have, the design will drill down into unit design. You'll then end up with unit implementations, and the units can be tested. And then you build up the testing on the right-hand side of the V to validate the various stages. Some of it will be done by review, which you're reviewing the architecture. That will normally be done by review, whereas the particular requirements functionality will be done by test, and obviously at a lower level, the unit test. And so I've kind of skipped a little bit forward. Once you get full right-hand test of the implementation and of the requirements, you then have to go through an integration test phase. That means that first validating your assumptions that were made on the target you're integrating with, and then run whatever tests are necessary to prove that that particular integration of this module is still working as originally designed in this particular product. So typically this is called like hardware in the loop testing, or it can be done in simulation as well. Depends on your development environment. The key to all of these things, the cornerstone to all safety projects, and the thing that I'm going to stress most in this presentation, is the traceability in these elements. In normal standard development methods, we go to great lengths to have good specifications, to have good test suites, etc. But what's completely different in safety environments is the rigor with which you treat traceability. Every requirement has a link to a test case. Every test case has a link to a requirement. Every design element, an architecture element, has a link to the requirements. And all the code has to be exhaustively tested as a result of these requirements and these test cases that are derived directly and linked. And that's why it's very important to use verified tools to manage the test cases and manage the requirements, because building all these links is very, very complicated. Typically, even quite simple. I mean, we have a TCP/IP stack developed to 26262 A-SIL B level. That has literally thousands of requirements to develop that stack. So somewhere coming on for nearly 10,000 requirements, I think. And to maintain that and maintain the related test cases is a huge job of work. And of course, you need to make sure everything comes together. So these are very important. This is the very important key point, is the traceability between these things that needs to be done. So now what I'd like to do is come on to the practical part of this presentation, which is to show how we're going to specify a very simple software component and see how that works practically in terms of these methods. So we're going to create a very simple software module. The customer's given us a specification. It should be a reusable software component, so they want to be able to use it in this product, that product. And its only job is going to be to flash a LED on and off every 10 seconds. This is not going to be, unlike safety projects themselves, this is not going to be a rigorous demonstration. That would take far too long for a webinar. That would take hours or days, maybe, I don't know. But this is the idea here, is to give you the idea of what the processes are. As you can see, this specification is pretty vague, really. It's not wonderfully accurate, so we're going to have to work on that to get somewhere. So before we start building it, we have to make some assumptions about the platform that this module is going to be integrated with. And so we're going to make some assumptions and we're going to document them. Our first assumption is this software module will be scheduled by a host system. The second assumption we're going to make is that the host system will provide a LED on function, the host system will provide a LED off function, and the host system will provide a millisecond counter function, so we can know what the time is in milliseconds, or the relative time in milliseconds. With these things in place, we can then start to build a module that could be reused in different systems by validating the core assumptions from which it would build. It is this kind of problem that led to the crash of the Ariane rocket, where after takeoff it crashed into the sea because they had a miscalculation because of an overrun, which was they changed the basic assumptions of the system but they hadn't got them completely documented or under control. They went from one type of microcontroller to another, and they ended up with an unexpected overrun. If they had defined their assumptions very accurately, they wouldn't have had this kind of problem, or likely wouldn't have had it. I mean, obviously, mistakes are made. But the core principle and part of the resulting study was to show that it's really important to have these definitions, understand the environment you're working in, and this should be clearly specified. So then, now comes the specification part. They use the term requirements in safety engineering. Effectively, this is the specification of the system. It starts from high-level requirements and goes deeper and deeper into very detailed requirements. This can also represent the specification that you can present to the customer to make sure the customer is getting what they expected from their contract when they wanted to take on this software. And so we're going to specify two simple requirements for this project. The first requirement is that the LED gets switched on every 10 seconds. And the second requirement is that after the LED is switched on, then switch it off. Now, technically, the customer original request to switch a LED on and off every 10 seconds could be interpreted in many different ways. It could be like switch a LED on for 10 seconds, wait 10 seconds, switch it off again. This is how we've interpreted it. We show this to the customer says, yeah, that's fine, that's what we meant. We want to switch a LED on. Once we switch it on, we want it just to flash and switch it back off again. So on we go, we've got a full agreed requirements with our customer. From that, we can skip straight to the test cases if we want, so that's not typically how the V model gets implemented, in that you should be going down and then coming back up. But there's actually no reason why an independent team cannot go and specify the test cases immediately. And the test cases from this, which we can map back to the requirements, are that the LED goes, test that the LED goes from off to on every 10 seconds, and test that if the LED is on, it subsequently is switched off. Depending on the level of safety required in the system, this test case development may be done by a completely independent team or even an independent company from the requirements development. It depends really on the type of project you're working on. But the principle remains the same. All requirements have to be covered by test cases, and all test cases have to be covered by requirements. And with these two test cases, we've done that, at least in our not completely rigorous example we're doing here. So from this, we're going to skip the architecture, the detailed design, and go to an implementation in what I would call a C-like pseudo language. Please, this is not a accurate C representation. This pseudo language automatically takes care of things like overflows and stuff, so we don't have to worry about that. And this is the simple piece of code. So the function is blinking LED, reusable component. We initialize the start time, and then forever we wait until the start time goes up by 10 seconds, 10,000 milliseconds. Reset the start time, then switch the LED on, then switch the LED off. This piece of code covers all the requirements, also all the test cases. If we run this in our development environment and we test the LED on function is called and the LED off function is called and the timing is about right, then this function should function. This should function perfectly. So not too complicated. Obviously, if you want to get very pedantic, you can start arguing about the details of this pseudo language, but again, this is not the point. The customer takes this code, he runs the tests, verifies that indeed the functions are called correctly, all tests pass. Customer then runs this on their target hardware. They don't see anything. They don't see any flash, nothing happens. What could possibly be wrong? Well, the first thing that could be, simplest thing that could be wrong is that the LED is switched on for too short a time to actually be visible. No time for this was specified, so we need to think about, okay, but that's not what we wanted. The customer really wanted to be able to see this LED. So then what will result is a conversation with the customer and the development team and try and work out, well, okay, we've obviously got something wrong in the specification here. And so maybe we come to an agreement with the customer, okay, what we actually meant was switch it on for 10 seconds, then switch it on for 10 seconds, switch it off for 1 second, then switch it back on again. So we realize, okay, we need to do that, but that's quite easy to change. So we can go into our implementation and we can simply go forever. While start time is less than 9 seconds, we switch the LED on. After that, we wait for 1 second, so until the start time reaches 10 seconds, we switch the LED off, then we reset the start time, and so this will have a 10-second period, the whole event. So there'll be 9 seconds on, 1 second off. This meets the customer's, it fulfills the requirements, it fulfills the test cases, so everybody should be happy at this particular point. The safety developer would not be happy at all at this point. For a start, you should never start by modifying the implementation. The first part is to do an impact analysis and find out what's wrong with the requirements. The reason why you can see that this is wrong is that you now have code in here that isn't matched to a requirement and doesn't have test cases to validate it. There's nothing to validate this 1 second LED on time that we've now specified. Even though it meets the current requirements and meets the current test cases, this code is not an accurate representation of that. So what should have happened is we should have gone back to the requirements, done an analysis, seen what's wrong, modified them, and then eventually modified the test cases, modified the design and the implementation, and then we come back and everything is consistent. And one of the big points about this is that going forward in time, if you develop a really good module, somebody might not have to look at it for 3-4 years. The personnel change, time goes on, people forget what's happened. The further you get from the completion of the development, both in terms of time and personnel, the more difficult this will be to maintain. But if you have full traceability in these things, then anybody can pick this up and find out what is going on. If they'd seen this modification, they'd be going, well, what is this code in here? What's it doing? There is no requirement for this. There is no test case. So what you have to do is you have to do an impact analysis to do this properly. And so we're going to do a requirements update to fix this. Every 10 seconds, we'll switch the LED on. That's kind of what the customer wanted. And then 1 second after the LED is switched on, we'll switch it back off. So we've updated the requirements. Obviously, that means we're going to have to review the test cases. There's links. We can see they've been modified. The impact analysis will show the links between the test cases and the requirement. Because the requirement's been modified, we need to look again at the test cases. So we review the test cases. Now we need to change the test cases. The test case one is that test that the LED goes from off to on every 10 seconds. And test that if the LED is switched on, 1 second later, it's switched off. Quite straightforward. All the links are in place. You can go and modify the implementation as we did. You'll end up with the same code. But now, the difference is that for that implementation that we saw, every single piece of code is covered by a requirement and by a test case. So anybody looking at that at 10 years in the future, a completely independent team, can do an impact analysis and modify it for some future behavior. But that's not necessarily the end of the story. So now the customer takes it, they run it, and they find that the signal is jittery, that this square wave, 9 seconds, 1 second, 9 seconds, 1 second, it moves by a few milliseconds here or there. And actually what they really wanted is something that's a nice square wave. So what are the sorts of things that could cause this? Well, actually, the implementation as such is not likely to be the cause here. The possible causes are the scheduling time of the host system, how often it schedules this software, that could create jitter. And also the behavior of the LED on and LED off functions, the rise time and the fall time of them, and how quickly they're able to respond to the call. So that means that to solve the problem of jitteriness, we're going to have to go back to the assumptions and change the assumptions the system is built on to be able to create an environment that you can now create a jitter-free system or an acceptable level of jitter. There's always some level of jitter. And so we modify the assumptions for the system that need to be guaranteed to get this level of jitter out of the system. And so we'll add some modified so that the original one that the host system schedules our software, well, we make sure it schedules it every 10 milliseconds to maximize the jitter at 10 milliseconds. We'll then also add some additional assumptions, assumption 3 and assumption 5 here, that the LED will be switched on in less than 10 microseconds, the LED will be switched off in less than 10 microseconds from making the call. And these additional assumptions allow you then to make a jitter-free environment. That's not the whole story though, because once you've done that, if your requirement is to have a jitter-free system, then that needs to be in the requirements. It needs to be in the test specification to be verified as part of the system. And so, although it is necessary to modify the assumptions to make it possible to make the jitter-free system, you still need to modify the specification and hence the test cases to be able to actually verify that the jitter is achieved on your target system when you integrate it. So the idea of this whole thing is to try and explain how when you move from a standard software development to a safety software, the requirement for rigor, the requirement for linking things is extremely important. Rigorous traceability between the specification, the design, the implementation of the test cases is the most fundamental change when going from standard safety software development to standard software development to safety software development. There's much more to it, and it depends on the level of safety you're trying to achieve in your system, whether you're going for the highest safety levels of flight critical software or A-SIL D or SIL 4 for industrial safety, or whether it's for a non-life critical system. You may have very different requirements in terms of the independence of the reviewers, in terms of the amount of checking that needs to be done at various levels. But regardless of which of these things you're trying to do, the core thing that allows you to do impact analysis so you can make changes, the core thing that allows you to make sure everything is done properly is this traceability between the specification requirements, the architecture, the design, and the test and the tests. Safety software, there are no shortcuts. There's an enormous amount of hard work you have to take into a lot of different factors like the qualification of your employees, the quality of the tools, you have to level of review, the independence of team members, depending on what is to be achieved. But the key thing I'm trying to present with this presentation is the fundamental difference in how you have to handle traceability between requirements, specification, test cases, and the implementation. So thank you very much for listening to that. I hope that's given you some food for thought, or at least given you some ideas for people who are not so experienced with safety software development.